G'day, I'm Paul from Polyman Astro, and welcome to my new YouTube channel. I assume you're here because you already follow me on social media, but if you happened upon this video because you were looking for astrophotography related content on YouTube, welcome, that's awesome. But please do follow me on either Instagram or Facebook using the @PolymanAstro handle, which you can see in the links below. Alright, let's get started. Cue that intro. My first video is on narrowband color palettes. It's based on a talk I gave at my local astronomy group, and the reason for it is a simple one. Most of the images there use DSLRs or one-shot color cameras, and they're used to taking straight RGB images. Narrowband's something a little bit different to them, and I wanted to demonstrate to them that the color palettes that we're choosing, they're still RGB, but they're telling us something very different to a color image. A lot of people like to call them false color. I don't really like that though, because it tends to suggest that the color in the image is in some way made up. While it's true that it's not what you would see with your own eyes, it's not false in the sense that the colors are telling you something very important about the nature of the universe. Before we talk about narrowband color palettes, it probably makes sense to talk about how our cameras actually make a color image in the first place. I know it seems counterintuitive, but let's start with a monosensor. A monosensor only captures in black and white, basically. All it's doing is photons are hitting it, and it's recording how many photons are actually hitting it over the length of the exposure. So a particular pixel is as bright as it is because a certain number of photons have hit it. It's color agnostic. All it cares about is the fact that photons have hit it. The way we get a color image from a monosensor is we put a filter between the sensor and the objective of the telescope, so that then all of a sudden only red light or only blue light or only green light is hitting that sensor. As far as the sensor is concerned, it doesn't notice, it doesn't care, it's just having photons hit it. But by putting that filter in front, we're ensuring it's only red or green or blue, and then we can put those three different intensities together and we'll get a color image. Okay, now's why that seemed counterintuitive, but it actually makes more sense to now talk about DSLRs and one-shot colors, because they are also monosensors. But unlike a mono camera, their filters are built right in on top of the sensor. There's this little, we call it a Bayer matrix, and it's basically millions of little filters, red, green and blue filters, right in front of the sensor at the pixel level. And they're generally set up as little red, green and blue filters in a 2x2 array, one red, two greens and a blue. What order that's in depends on the camera, but it's generally a red, a green, a blue. So it can get all those intensities of the different colors, red, green and blue, all at once, and straight away it can form a color image. So at the end of the day, they're all monosensors, they all have filters, it's just, are they built on top of the sensor, or do we have to put one in front of it? Okay, so when we get into color processing, using whatever processing software we use, we take that intensity of red, that intensity of green and that intensity of blue, and we overlay them on each other, and we get all those wonderful array of colors and hues that we're used to seeing in a color image. Okay, now that we have that understanding, we can start talking about narrowband palettes. The advantages of a monosensor are that we can put whatever filter we want in front of the sensor. We don't have to just rely on the visual spectrum that we're used to. We can use what are called narrowband filters. They have that name for a very specific reason. They restrict immensely the wavelengths of light that get to that sensor. We tend to use three main filters in narrowband imaging: hydrogen alpha, oxygen 3 and sulfur 2, which I'll probably call H, O and S throughout the remainder of the video just for brevity. And you can see from this image here where they fit on the visual spectrum. So O3, for instance, sits between blue and green in the cyan kind of region, And here's an image from my unmodified DSLR of the Tarantula Nebula, and you can see that it's quite cyan looking. That's because there's a huge amount of oxygen there. The H and the S both sit in the red part of the spectrum. So if we were going to create an image that was kind of true to life, and we put these filters in the correct part of the visible spectrum, we'd have an issue in terms of contrast, because H and S are so close together in that red end, it would be very hard to tell them apart. So what we do, well, we've got three filters, right? And we've got three main colors, primary colors, RGB. Why don't we put one of the filters in red, one of the filters in green, and one of them in blue, and we'll get a nice color image. And that's exactly what we do. So the notation that we use to name our color palettes is purely based on which filter we put in red, which filter we put in green, and which filter we put in blue. So SHO, for instance, the most common of the palettes, is named because sulfur goes in red, hydrogen goes in green, and oxygen goes in blue. There are 6 main palettes. I'll call them the pure palettes, and they're purely dependent on the fact that we can put 3 of the filters in red. Once we've chosen one of them, there's 2 left to put in green, and then 1 to put in blue. So 3 times 2 times 1, that's 6. In reality, there's an infinite number, because there's no reason that we can't put all 3 filters in red in some percentage, different percentage in green, and a different percentage in blue. So nearly infinite number of possibilities, really. But we're just going to look at the 6 pure palettes in this video for simplicity. Okay, and those 6 pure palettes are named, as I said, based on which filter goes where. So here you can see the Great Nebula in Carina, and I'll run through those 6. So there is SHO and OHS, and you can see they're kind of inverses of one another in terms of where the colors sit. Then we have HOS and HSO, and they are again inverses of one another. And then finally we have OSH and SOH, inverses again. Okay, and you can see the very different colors that are produced, and we're about to talk about why that's the case with a little bit of color theory. So here's an image of the Statue of Liberty Nebula in HOS. So I've used a palette that's common with ESA and the CFHT, which is the Canada, France, Hawaii telescope, and it's quite different to the Hubble palette. The idea here that I want us to zero in on is what can narrowband images actually tell us scientifically. So if we look at this image, there's some pinks and some yellows and oranges. What does that actually mean? Well, let's pop a color wheel next to it, as you can see here. And remember, red is H, green is O, and S is blue. So we'll remember that. And then let's have a look at, well, where do these pinks or magenta-y kind of colors come from? Well, if we look at the color wheel, that's the interaction between red and blue. The fact it's more pink would suggest it's got more red than blue. So since red is H and blue is sulfur, there's more hydrogen than sulfur, but it's an interplay of those 2 gases. So those tendrils are hydrogen and sulfur. The fact that the nebula to the left is quite orange would, looking at the color wheel, suggest that it's an interplay between H and O, because it's red and green. The fact that it's orange would suggest, again, there's more red, there's more hydrogen than there is oxygen. So unsurprisingly, we're seeing that hydrogen does tend to dominate this particular image, as it does with most images. It's the most common element, so it does tend to dominate. But from the image, straight away, we can see regions where there is more hydrogen and sulfur, there's more hydrogen and oxygen, and in fact, we might be able to find regions in the image, not so much in this image, but in others, where there's an interplay between oxygen and sulfur. So bear that one in mind, oxygen and sulfur, because we'll come back to that one later. It does occasionally happen that the hydrogen and the sulfur don't always perfectly overlap. There are differences in their distribution. Okay, so scientifically though, these colours, these hues, tell us very important stuff about how the gases are distributed within a nebula. Alright, we're back to my favourite image again. We're back to the Great Nebula in Carina. This one is in SHO, the so-called Hubble Palette. And you'll notice that there's all sorts of hues in this image. If you look around the outskirts of the image, just like in the Statue of Liberty Nebula, where all those kind of tendrils and I guess they look like little shock waves all the way around the outside of the nebula, they're red in this case, reddy orange, yellow in this case, because again, there's an interplay between red and green, and in SHO, that's sulfur and hydrogen. Okay, so the two of them are interacting. You can see there's regions where it's more green, there's regions where it's more red and orange. So in fact, sulfur in some cases does tend to dominate over the hydrogen, and it's quite asymmetric, this nebula. It's quite nice. On the right of my image, it starts quite red and it moves to the yellows as we go from right to left. In the center of the nebula, you can see that there are these blue cyans and green cyans, and you will see regions closer to the Keyhole Nebula, that brighty kind of bubble-looking section, middle right. There's regions there where it looks more magenta. Okay, and that's not just the stars that are looking magenta. If you look closely, the actual nebulosity is magenta. That's where I'm saying that this is a really nice example that shows that hydrogen and sulfur don't always overlap. Okay, here it is in fact sulfur and oxygen that seem to be overlapping, and there's very little hydrogen in the center region there. This is a similar kind of looking image to the Tarantula Nebula. If you ever look at the Tarantula Nebula in SHO, again you'll see these magentas appearing. So it does happen. Hydrogen and sulfur don't always overlap, but there are definitely around those shock front kind of regions. That's where you tend to see the sulfur and hydrogen for the most part. Okay, so the distribution of the gases within the nebula are very easy to see using these palettes. That's why these pure palettes are so useful. So the final bit for this section on the kind of color theory and what the hues tell us about the gases, this is kind of the key part of this whole video really, this section. How can we actually use these palettes to do some science? In my talk, I had a little bit of an interactive session where I actually showed some pictures and asked the audience to tell me what they noticed. So here's your chance. Here's an image of the fighting dragons of Ara, and you'll notice, I want you to notice two things in particular. If you look at the dragon egg towards the bottom right, you'll see that there's a blue kind of ribbony looking thing, like little tendrils around the dragon egg. This is an SHO image. I want to know why those tendrils are blue. What is it that makes those tendrils blue? And the other thing I want you to notice, if you look at the dragons are dark clouds that aren't actually an emission nebula. They're more a dark nebula. The emissions around them. And if you look around them, the outline around the dragons, it's yellow-orange. Why? Tell me in the comments why you think the tendrils are blue and why the outline of the dragons is yellow, given that we're in SHO. It's your chance to actually use what you're learning here to have a look at an image and try and do some science. What's the distribution of gases in this picture? So for the final part of my talk, I'm going to get a bit contentious, I think. You've just seen examples of the 6 pure palettes, the main palettes that we use for narrowband imaging, and you've had a chance to look at why they're so important and what they can tell us scientifically. So it's a real bugbear of mine when I see all over the internet the Hubble Palette. The problem is it's not really the Hubble Palette. If you go and have a look at the pillars of creation, you go and have a look at the Mystic Mountain and the center of the Lagoon Nebula, do you see blue and gold? I don't think you do. You see a wealth of subtle hues throughout the whole image. And I've tried to show you with just the pure SHO palette, you can indeed get that wonderful assortment of hues. It does take a bit of work. I don't want to go through that today in this video. I will do a short processing video to show you the key step you need to do to make your SHO images have that wealth of and breadth of hues. Otherwise you really will just get a green image or a blue gold image. So that's a future video, because I don't want to get through the processing on this. I just want to show you the narrowband palettes and what they can tell us. That was the whole point of my talk when I did it. But I do, in this final bit, just want to mention my bugbear with the Hubble palette, and you see it all over the internet. I won't name sites in particular. I don't know where it's come from. I'm trying to research where this belief that the Hubble palette is blue and gold came from, because you lose so much information. The image that I've got up at the moment, this blue gold image, it's my same image I showed you before of Eta Carina. Beautiful. I'm not going to dispute that the blue gold is a beautiful choice of artistic palette, but it's lost that scientific information. All of a sudden, if you look at this image now, there's no way you could tell me that there's an asymmetry in the Eta Carina Nebula from right to left in the image here. It's only when you look at that SHO image, that processed image that keeps all that information in it, that you can see that there is this asymmetry in hydrogen, sulfur and oxygen across the nebula. And I put this to the Ice in Space website, and one of the guys there came up with a beautiful hypothesis on what that might be. And it's a galactic scale, what's the word? A galactic scale issue. The fact that we live in a spiral galaxy and those spiral arms rotating causes differences in pressure at the galactic scale, and as that sweeps across the arm, we see it in the nebula right here, that it's firing off and heating up hydrogen first, and then as those stars burn out and cause supernovas, that's when something like sulfur is produced. So there is this asymmetry in these spiral galaxies, and we can see it even across a nebula. No way to prove that theory, I suppose, but it's an interesting hypothesis, and I think it is reasonable in this image. Whether it's true or not, the point is that that kind of asymmetry would be lost in the blue gold Hubble palette. So don't kill the green. I promise that's it for today. Hopefully you feel sufficiently nerded out, and if that's the case and you'd like to see more content like this in the future, please consider subscribing to my channel. Don't forget, follow me on Instagram or Facebook. I'm Paul from Paulie Man Astro. Thanks for watching.